All right, so welcome everyone, officially from my side. Most of you probably got an email from me, but don't know who I am. So my name's Sarah Barber. I'm actually from Switzerland and I've got nothing to do with Brazil. I'm the head of the Wind Energy Innovation Division at the Eastern Switzerland University of Applied Sciences. I'm also president of the Swiss Wind Energy R&D Network. And what I want to do today is quickly just give you an introduction to who my team is and what the Swiss Wind Energy R&D Network does. Then I want to go through a few administrative things related to this event in the next week and introduce you to the lecturers. And then the first lecture will start at about 10 past. Can I actually just check, is Ingrid there? Are you there, Ingrid? She's the lecturer for the first part. She doesn't actually seem to be here. So let's just hope she's going to turn up in the next 5 or 10 minutes. Okay, so I'm going to do the introduction. If she's, or maybe I'm going to write her a message quickly to make sure she's okay. Okay, and then I'll just go ahead with my part. So just to what I'm doing at my university in Switzerland. So we apply interdisciplinary research to develop inspiring, innovative solutions that can be adopted effectively and sustainably by people to contribute positively to the wind energy sector. So we do quite a lot of stuff on digitalization, but we focus on people as well, which is why we like to organize workshops like this. And yeah, our main focus, as I said, is on topics of digitalization. So we do things like develop smart measurement technologies. This is a pressure measurement device that we develop. We do lots of work on knowledge engineering and data modeling. So how to structure data in a way that artificial intelligence can use it easily. And we then do lots of data analytics and AI. We have some projects on digital twins and decision support. And then we're quite into the topic of data sharing and making data fair, which means findable, accessible, interoperable, and reusable. And we try to bring together people with data to solve problems. Our research has got to do with flow modeling in mountainous terrain. In Switzerland, we have lots of mountains. We also look at rotor blade aerodynamics with our measurement systems. We've got some projects where we're looking at the dynamics of the whole system. Then we research into different collaboration methods, so a bit with social scientists, with social science, and then we have diversity inclusion topic as well, because it's important for us to include lots of different people in research. And the Swiss Wind Energy R&D Network, you'll have seen that the invitation to this event came on our website. So we're trying to bundle Swiss research and development wind energy capabilities, but we're also trying to promote relationships and collaborations with other countries. So this whole thing with Brazil and doing this workshop is quite important to us, because Switzerland's quite keen on expanding its services to Brazil. And so we have quite a lot of companies who have innovative things that they do, which could be used for helping Brazil reach its offshore wind energy goals. We have this project called We Do Wind, which is how this whole collaboration with Brazil started. And so We Do Wind is a method that we've developed for actually bringing people together with data and solutions. And on this picture, you can see we have this idea of challenges. So we have challenges like data science challenges where people provide data, like wind farm owner operators provide data, and then students and researchers and data scientists try to solve the problem. And the reason that people take part is because the data providers, they're looking for new solutions, and the solution providers, they're desperately looking for data. So the idea is to do that all together. And this collaboration with Brazil actually started by thinking about what challenges we could do together. So far, we've had 2 really interesting projects. One with a company called EDP in Portugal, who shared some data. We published this paper where we looked at different algorithms for fault detection. We did a second one with a company called Wingy in Switzerland. We've just submitted a paper learning about data sharing and about evaluation of different models. But then we've got 3-4 more running. So we have with a company called Cubico in the UK. We're sharing some data. We're working together with a professor in the US who's written this book about data science for wind energy, and we're looking at structural health monitoring challenges with a Swiss company. And then we have the wind energy in Brazil space, which basically just aimed to bring lots of people together who are interested in solving the challenges of implementing offshore wind energy in Brazil. And that's basically where this whole workshop idea started. And so what we do in the Brazil space is that we provide a neutral, independent platform for you to all to come together and discuss different challenges to accelerate wind energy in Brazil. So we are trying to write a paper as well where we're summarizing the main challenges, and we're also trying to reach people like you. So that's why we're really happy that you're all here. Now some administrative things. First of all, so there's only one Microsoft Teams invitation, which is valid for the whole week. Most of you signed up for every day, so you've just got the whole series. Some of you signed up for individual days, so I just sent you the individual links to those days. The other rule is that please try to turn your microphones off if you're not speaking, but I am happy to see as many faces as possible. So feel free to keep your camera on while we're speaking. As I said before about the recording, some lecturers will record their lectures and some won't. The ones who do record, we will put everything on a YouTube channel and make it available to you all afterwards. And we've got, I'm going to send you this link in a minute, but we have a link to a shared folder where we're going to put the presentations and any documents you need for the exercises into. And then I won't be present for the whole time, so I will be giving a lecture later today after Ingrid, but on Tuesday, Wednesday and Thursday I won't be present, and I'll be back on Friday later afternoon. But if you need anything from me or any organization related things, just write me an email and I'm basically available at all times. So to the time plan for this week. So we have today we have after my introduction, we have Ingrid, who's going to give you an overview on the Brazilian wind energy market. And Ingrid's now here, I'm glad to see. So hi. And then in the afternoon, I'm going to give you an overview of the basics of how wind turbines work, basically. And after every lecture, we have a workshop. So the idea is roughly 1 hour input and 1 hour group work, or you're working on a problem and then you discuss the solutions together. And we'll have a small 5-minute break between each session. And then on Tuesday, we have Marina Cavalli, who'll be talking about loads and blade design. Then later in the afternoon, we'll have Heloisa and Wilson, who'll be talking about composite materials. On Wednesday, Victor is going to be doing both sessions on energy conversion systems and grid integration. And on Thursday, we have Yoshi, who's going to talk about wind resource and measurements. And then we have Raphael, who's going to talk about layout and wakes. And then on Friday morning, we have Carlos, who's talking about condition monitoring. And then we have a panel discussion where all the lecturers will be telling you what they do in their research, but also then summarizing and discussing the challenges specifically related to Brazilian offshore wind energy. And maybe the lecturers who are here right now could just quickly say hi, and just say where you're from. So maybe Yoshi, I'll just do it in the order that I can see on my screen.
Yes, so Hello, everyone. So I'm Yoshiaki, professor from Federal Institute of Santa Catarina in Florianópolis. So my lecture is going to be on Thursday for with the resource and measurement. So hope you see you all there and share my experience.
Thank you. And then Victor?
Hello, everyone. My name is Victor. I am professor at the Federal University of Minas Gerais. My lectures are in Wednesday. Yes, I will talk about the electrical parts. Yes, I am professor in electrical engineering. So we take a look of the system of this conversion system. Then it's very important first this first day that Sarah will present the turbine, yes, and tomorrow. And in the Wednesday, we will look for the electrical part.
Yeah, great. I might even be attending, actually. I need to learn more about the electrical parts. And then I see also Carlos.
Hello, everyone. I'm Carlos Souza. I am professor at the Federal University of Santa Maria in the south of Brazil. And I'll be talking Friday about condition monitoring. It's a very wide topic, and I'll try to see what I can, show people, mostly students, I see. Okay, and I think we have a great discussion.
All right, thank you very much. Apart from Ingrid, are there any other? There's no other lecturer here right now, is there? Is there anyone else is here that I missed? No, the others couldn't come right now, but you'll meet them then when I give their lectures. Yeah, so I'll hand over to Ingrid now, and she can introduce herself and then start her part of the lecture. Ingrid, just before you start, I've got a question. I'm going to leave. I'm going to leave now, so the recording is probably going to stop. So if you happy to record your part, can you press record again? You know how to do that?
I don't know if I can. I'm actually working my corporate account because Teams, the free version now, it's a little bit, let's say, tricky. So I don't know. I wouldn't have problem to record, but I don't know if I can.
Oh, you don't know if you're allowed to, you mean?
Yeah.
Oh, okay. Yeah,
because
then don't record it.
I'm also not from the same company as you. This is the problems with Teams sometimes.
Okay. So I'll just record my part. And the second question is, do you need breakout rooms later? Do you need me to come back? Because I have to open them for you when you're doing your workshop.
I think it would be nice to divide people maybe in small groups to do like my exercise.
Yeah, okay. So you do.
But if it's a too huge problem, it's fine as well.
No, I just need to know. I just need to come in and do that for you because I don't think you can do it yourself.
Yeah.
Can you tell me when? Can you just? Actually, you can call me from inside Teams. If you go, I'm just going to share that screen. If you go to the people, you can actually because I'm online. You can just call me. I think from this list, I'll be on this list here.
Yeah, sure.
I think you can just call me and then I'll quickly jump in.
Okay.
All right.
No problem.
Then I'll hand over to you. And yeah, everybody else, I'll see you all later today, and get in touch if you need anything from me. And enjoy it. See you later. I'm assuming you can share your own screen, Ingrid, yeah?
Yeah, sure. I'm just having a look in the folder now to share my screen. I think I noticed with important. Sorry, guys. I'm a little bit late because of work. So you guys know how in consultant things work sometimes. Okay, just a second. lectures. Oh, this thing is okay. I think I know how to manage this. But this is Teams. Okay, guys. So I think I won't be. I don't know if I'll be able to see you during the presentation.
Yeah, so I think the rule for, I forgot to say that as well, like anybody, if you can answer questions, you do it. If you want to ask questions, write in the chat. But if she can't see us, like for example, you can't see your screen, like I think it's fine if people want to just turn their microphones on and ask a question in the middle. Like for me, I prefer if people do that than if
Yes, because I'm using only one screen.
Yeah. So feel free to do that, everybody, I think, and that would be, otherwise ask a question at the end. Okay, good luck. See you later.
Okay, thanks, Sarah. Bye.
Bye.
So, hello, everyone. My name is Ingrid. I'm currently living here in Hamburg. I'm working as a renewable energy consultant at Wood. And before moving to Wood, I used to work as an independent consultant for offshore wind for Brazilian projects. So I believe I'm kind of expert in this market here in Wood. Let's say I divide my tasks. Half of the time I work with offshore wind market, half of the time with onshore now, and I changed it a little bit. I used to work more with market studies. Now I work a little bit more with technical due diligence, which sometimes includes some part of technical advisory. So if you have any questions about life in consulting, or even what's like the difference between the two kinds of consulting, feel free to ask at the end of the lecture. So because I think our public here is more related to the university, I believe I chose some topics that might be more interesting to you. If you have some idea about offshore wind, maybe this will be like really, really basic, but I hope you enjoyed the lecture as well. So those are the 5 topics of our lecture that I expect it will last like 40 to 50 minutes, and then we have an exercise in the end. And I think this exercise will be very nice to check like your previous knowledge about this industry, and even like to together with what we are seeing now. I'm not quite sure if everyone here is from Brazil or not, but if we only have Brazilians, we can also like talk in Portuguese. I don't mind. Okay. So because nobody said anything.
I think most people are Brazilian, Ingrid. I think most are. You may ask in the chat.
The thing is, I don't know if I can ask in
You
the
cannot.
chat because, yeah.
Let's go in English. Okay. Well,
Okay, no
how you think
problem.
is better? How you think is
Yeah,
better?
yeah.
Okay?
No, I can keep in English. I'm fine with keeping in English. Okay. So I think that the first numbers that I wanted to show you all are the numbers for the global wind report from GWEC. I believe that all of you might know what GWEC means. Is the Global Wind Energy Council. Um, they have like the data of all the world for onshore wind and offshore wind. And this is a graph of the historic development of total installations. Okay, this graph, it has started in 2001. And just a spoiler, actually, offshore wind, the first wind farm was 10 years before that. but you can have a look, and it was like, let's say, a very small percentage of offshore wind back then. But it's a market that has been increasing, as you can say, according to the total development of installations. And the perspectives are really good because Asia has been, I didn't put a graph here, but you might know that like almost half of all the installations last year, if you have curiosity and want to check this report later, you'll see that a very high amount was installed in Asia, especially in China. And Europe, of course, is still like the leader in total installations. The country with more installed offshore wind capacity is the UK. After that is Germany. So, and Europe is a big leader in general, and also the United States has very ambitious plans to keep like their goals, although it's not in a federal level as most of the other countries. There are some states that they really want to become more green. So we expect that probably maybe in 2030 they will have like a huge percentage of the whole offshore wind installed in the world, and we hope that soon we also have some percentage in Brazil as well. So I wanted to show you a little bit about the context here um, of about offshore wind, because sometimes I used to hear a lot in Brazil that, oh, this is a very distant reality, but you can see that this concept has started since 1930s, and in the 70s there was also like another proposal. And if you can like see this date, it's also, let's say, a similar date of oil and gas development in offshore oil and gas. So they were like combining this idea. And we had like lots of crisis, energy crisis. Here in Europe, the energy crisis is very high. And for instance, in the UK, due to the offshore wind, they can like they can low a little bit the cost of energy. And offshore wind is not that cheap, but the gas prices, they are like really, really high because of the war, and probably because it's a commodity. The prices of all the oil products, they are very high everywhere, except if you have like some subsidies, what's happening now in Brazil. So this is a way of developing those kind of technologies to put like more uh, to invest more on them. And this is good because eventually there are some studies that I believe in 5 years, it is expected that the cost, at least in the UK, for onshore wind and offshore wind, they won't be that much different. So while we are developing the cost, yes, at the beginning, the costs, they are like very high, but they can reach sometime like this break-even point. So talking a little bit about the history of offshore wind, the first wind farm, the first turbine was installed in Sweden in the 90s, and in 1991 it was installed the first offshore wind farm in Denmark. The name of this project was Vindeby, and Vindeby was already decommissioned. It wasn't a huge wind farm, but it was a very interesting case because of this project. The scientists, they could understand a little bit better how the turbines would perform in this environment. Because one thing is what we are doing in the lab. We do a lot of simulations, studies. But the other thing, for people who has some background for naval architecture or everything that involves the sea, you understand that sometimes what we consider in our simulations might be a little bit more different in the real life. So, continuing the topic, in 2007, there was the first, uh, let's call it prototype of floating offshore wind was installed in Italy, and 10 years later, they installed like a 5 wind turbine of floating offshore wind in Scotland. And this is a kind of trend here in Europe, because I don't know if you guys know, but in the North Sea, we have some regions with deep water, and we also have like the knowledge of the oil and gas industry that was developed here, like in Norway, in the UK, here in Germany. Unfortunately, we don't have that much oil to explore. But this is also a nice way to develop a whole different industry. And I don't know if you know something about the naval industry, but it's an industry with lots of downs and some peaks. So it's also a way of absorbing all those very high skilled professionals. We see sometimes in Brazil that people, they are like working on banks, working in very different areas instead of working in the area. And this is a good thing of offshore wind, same as like the oil and gas industry. You see a lot of the naval architects or naval engineers, which is the case of Brazil, working in this industry. And it's also a very, let's say, multidisciplinary industry. Like not only engineers, they might work on this industry. Also, of course, lots of people from STEM and lawyers and accountants and business administrators. So I would say that wind energy is a very multidisciplinary industry, but offshore wind sometimes we involve even more people, because we need the people who studies the sea as well, like oceanographists, um, even sometimes, let's say, um, fishing engineers, which is something that we would never expect for wind energy, naval architects or naval engineers, and so on. Okay, so I believe here are some lessons learned, and there might also be some of the advantages that we have in offshore wind, because probably, like, if we have a look in the project Vindeby, it was very close from the shore. And one of the, let's say, one of the first ideas of installing in the sea was to save space in the land, especially in Denmark or in Netherlands. But but developing offshore wind, we could also like see some very interesting outcomes. That winds, they are usually stronger and more uniform at sea. The turbines that we can install in the sea, they are more powerful. They can also be bigger. We also have some logistics challenges. But for instance, when we're installing an onshore wind farm, we also need to take into consideration the roads, because sometimes they are like very remote places. And for offshore wind, we can have like the supply chain developed close to the ports or to the construction yards. And then the logistics, of course, will be a little bit more different and sometimes challenge when you're like doing the installation. But we always have to remember that sometimes, like the naval industry, they already know how to solve those problems, especially because of the oil and gas industry. Also, another very important aspect is the reduction of noise and visual impacts. Even though offshore wind also have some, let's say, sometimes depending on the communities that are located close by, the people there might not feel that inclined to have those projects, but those projects, they can also bring some benefits like social projects. You can also like educate the people there to work to have a better life. And uh, like for instance, I live here in Hamburg. In Hamburg, I can see some wind turbines in the city. I don't know if they are in the city or if they are like in a very close place, but I can see them. I do. I actually find it's nice to the landscape, but it's not everyone that has this idea. And I live far. I don't hear the noises. But in this case, of course, like some animals, they might be a little bit harmed, but not for humans. And unfortunately, animals cannot communicate on this matter. And another very interesting aspect is that about 80% of all the cities, especially in Brazil, they are located closer to the shore. So to transmit this energy, we will need less transmission lines. So the transmission lines, they might be concluded faster because instead of needing, I don't know, 3,000 or 5,000 kilometers of transmission cables, if you're developing a project in, let's say, in the state of Rio de Janeiro, maybe you'll need 500 kilometers of cable at most. Of course, like we're going to have some other challenges because those challenges, those cables, they will need to be underground, but we will need to build a shorter transmission line. And as I mentioned the case of the UK, another lesson, and this is for everything in technology, the more that we develop something, the cost of that ends up decreasing. And this is the case of offshore wind. The costs at the beginning, they were very high, but with some subsidies and also these lessons learned that we have now, we are building more efficient projects. Although it is expected that the cost of the projects, they might be a little bit higher, these costs are not only for offshore wind or wind energy. It's for everything in the world because of the price of the energy and also like the steel problems or magnets or rare earth. But this is another topic that maybe we might talk on Friday when we talk more about those challenges. So uh, lots of people sometimes, I don't know, like 5 or 6 years ago, they used to say, offshore, why are we going to develop offshore wind energy in Brazil if our country is so big and we still have lots of space to develop onshore wind? But Brazil is, let's say, it's a place that really has lots of possibilities, even for non-renewable and also for renewable. We have a very big sea area. The sea area is about 2/3 of our land portion. We also have excellent wind resources, both onshore and offshore, especially in the Northeast region. And we have a very big estimated theoretical potential. It's really, really high. It's like almost 10 times. Of course, this is the theoretical. When we start doing some restrictions of places that we have actually the technical potential and other places that we need to exclude, this potential will drop. But as you can see, like 480 gigawatts or 748 gigawatts, even if we have like only 10% of this available, it's basically what we spend in electric energy in the country. So, and energy might also be a driver to developer. There were some researchers that they were saying that the country didn't face like a recession because the economy was really, really bad. But what happens if the economy starts growing and we need energy and we cannot fill our demand of energy? We will need to reduce the energy consumption as we did in the 2000s. And this might also, let's say, might also affect the economic growth. Another very important aspect of Brazil and very interesting is that we have a very strong record on developing renewable energy projects. We have a very clean electric mix, and I dare say also an energy mix. And this is also due to the technology that we developed. We have some Brazilian companies like WEG that works in the wind energy supply chain, and they are also one of the suppliers of those international companies, at least for projects in Brazil. We also have Aeris, which is a company that produces blades, and Aeris exports blades for Europe and the US as well. And another thing that might really be, let's say, a differential to offshore wind is that we have a very well-established oil and gas and also onshore supply chain and a very strong track record. I don't know if you guys know about the oil and gas industry in Brazil, but lots of very important technology that they are used all around the world, they were developed in Brazil, especially for deep waters, which means that we really have very good people working in this area. And probably in case if they want to, they can migrate to offshore wind energy. Sometimes, of course, the projects might be a little bit different because of the scale, but having all those bases might be very helpful to the development. Well, guys, unfortunately, the table it's not updated, but when I send the file to you, you'll see this all updated. And Brazil is actually a very, let's say, it's a country that all of the companies around the world they are having a look. And in this map, that here is a little bit small, from IBAMA, we can see all of the projects that all those companies they intend to develop. Of course, most of them they are like under some overlapping, but we can see some players like CIP, which is a company from Denmark. We see Shell. We see Total Energies from Europe. We see Ocean Energy, Ocean Winds, that they also have a very big interest on developing the market in Brazil. We see Coral Generation, which is a company that has lots of projects in Asia and also some in the UK. We see Iberdrola, that is also a good leader of the market. And all of those projects, they are about, like, of course, we have the overlapping, but the capacity of them is 170 gigawatts, which is the capacity that our network has of installed capacity. Well, I don't know what happened to my presentation, but I can keep on going. About the current regulatory framework, in Brazil, as I don't know if you know about that, but it's a market in the early development stage. So we still don't have auctions for this market or for leasing the areas. We have, let's say, regulation uh, being developed. We have maybe some of guidelines, but they are like very, very in a early phase that we are going to have some ordinances that they will define them more, especially the rules for EPE, the Energy Research Company, and also ANEL, the Brazilian Electric Energy Agency. They are still being under discussion. And there was a very interesting discussion that although at first the regulation from ANEL was only for wind energy, they are changing this. The new resolution regarding renewables, it will differentiate onshore wind and offshore wind. We also have some guidelines from IBAMA, and those guidelines, they might move according to what happens in the, let's say, in the first project description that the companies they send about the project, because we have to consider a lots of environmental things in Brazil that in some markets they are not considering as that important. For instance, we have a very strong regulation regarding like the um, the threatened species, for maybe benthics, for archaeological sites, and also for birds as well. We have migration of the birds, and also regarding the visual impacts, we don't have a defined limited yet. This might go in some of the guidelines provided by EPE or maybe ANEL about the minimum distance for the coast. But we know that in Brazil, we also have a very important aspect that is tourism and also fishing. And that's why the social aspect is very important to be discussed. There are some projects that they are already talking to all the stakeholders, and sometimes they might face some difficulties because the local population, they don't want them to develop those projects because of the it might jeopardize the sightseeing of the region. It might change the economy, but this is a very interesting job that the environmental agency or even the projects they need to do. And this is not actually something strict to offshore wind, but also for hydro energy. A lot of people they need to do that. I don't know if you guys remember, but some years ago we had a very shocking incident that a native, he used a huge knife and stabbed an engineer because of Belo Monte. So we need to negotiate, we need to present, and we also sometimes we need to have alternatives to those issues. And the other regulation that we already have now, it's the regulation regarding the Navy. And in the Navy, I don't know if you guys know, but the Navy is actually responsible to map, let's call it, to do like the charts for everything that's on the sea, that's under the sea. And so this is a very important agency that relates that takes care of offshore wind, because the thing is, in Brazil we don't have yet a maritime spatial planning, and there are lots of countries that they are still lacking that. But this is a very important mechanism, because you can do a kind of agreement with all the stakeholders, because you can you can say, oh, this place is a port area. So of course the Navy already have some standards, like that you cannot build anything from 5 kilometers in the way of the port. But the Navy or some or the transportation agency for naval aspects, they can establish that, okay, we might need to have a corridor for ships because we're going to have those huge farms, or we cannot build anything here because this place, it's a military zone. We do some military training, or even sometimes the environmental aspects, uh, because when we talk about, let's call it, protected areas. Depending on the degree of this protected area, probably even the Navy needs to do um, some inspection of that area. So they will actually have a lot of they might play an important part to say to the developers of this project, saying no, you cannot build this, because unfortunately, because we don't have this maritime spatial planning, sometimes it's, let's say, we have the lack of the information, and this is not restricted to Brazil, but because we have a huge area, this might impact us most. And regarding the other regulation that will come, the government is defining how they will proceed with the way of, let's call it, seabed lease. It's not actually seabed as it is in the UK. In the case of Brazil, we call it a prism, because in all of that, in that prism area, it will be dedicated, but because it is a territory of the nation might probably need to charge, as they do with other industries such as oil and gas or mining. And one of the thing is that we have two kinds of regulatories um, mechanisms that they are under discussion. We have one that is a decree, and this decree already mentions some of the agencies that we know that their involvement will be very important in the future, but we don't have the specific guidelines yet, like the Petroleum Agency, maybe the Ministry of Tourism, the Ministry of Telecommunications, because we have cables and the sea, and also the Ministry of Agriculture, because of this fishing farm, and also the Air Force, because the Air Force, we have some criterias for onshore wind, but very we don't have them very well established for offshore wind yet, but they might get also under the discussion. And now I wanted to talk a little bit about the synergies with oil and gas and onshore wind and other industries. And in this case of the synergy is very interesting, especially because we have, as we know, in the case of Europe, we have lots of developed oil fields, and those oil fields, they are reaching the end of life, and also, let's say, we're trying to get rid of the oil, at least for energy purposes. And this is, let's say, offshore wind can absorb the professionals and also some of the companies. Now, I don't know if you have already noticed, but we have lots of players that they used to be oil and gas companies, and now this is, let's say, a bad way of a company to introduce themselves. All of them, they are now energy companies like Shell, Total, uh, even Petrobras. They are migrating. They are probably going to develop some projects with Equinor in Brazil. And it is a big business. It is a very important business, and they are not that far behind. And we can see that, for instance, for a company that doesn't have any knowledge of the ocean, you might have another kinds of challenges that those oil and gas companies, they are already prepared. We also have some companies that they have already started the offshore wind business for so many years, like Ørsted or Vattenfall. But it's very interesting that those companies, they are not already in Brazil. So are they joining? Are they not joining it? We might need to have a look on that. Maybe they are waiting for the first public call for auctions for those areas. Or maybe they don't think that Brazil might be a very interesting market for them to go in. And the synergies are also for the onshore wind because the supply chain, lots of parts, let's say we already have some technology that they need to be adapted. And in this way, they they might we might need also their knowledge about aerodynamical or also the structural knowledge of towers. So they might play also a very huge part. And another thing is now the green hydrogen. Um, there are some concepts there. I believe that there are some case studies here in the North Sea that they are considering when they do the decommissioning of the old um, oil and gas platforms. Of course, they will try to remove as much as possible. Maybe the dismantling will be 100% or not, so they can feed the energy that they will need, because if you don't dismantle everything, you still need some pumps to pump the oil with water, which is mainly water in this case. So you can install an offshore wind turbine to, let's say, use this energy, or you can also use this structure as a hydrogen hub if the resources in that region there are very good, and they might allow you to install a park now. So I think actually it was faster than I expected, and I want to know, guys, if you have any questions about it.
Ingrid, hi.
Hi.
No one asked you, then I will do a small question. You
Sure.
talked about the Brazil, that we don't have already the regulatories or something like that. And can you talk a bit more the situation in Europe, the projects that you work or something like that?
Yeah, sure. Well, here in Europe, the things they are a little bit different because it's a market that we have developed. We have a very huge target, very ambitious target, and we also have problems in the industry. Uh, we have we have lots of problems sometimes with turbines, either onshore and offshore. Nothing is perfect in the world. But we already have the mechanisms to develop this industry because we have the energy acts. The thing about the thing about Brazil sometimes is that because the legislation doesn't cover it, and this sometimes, let's say, was a little bit of a fight between some of the stakeholders that they say, oh no, because it doesn't exist a specific regulation, but there is one for wind energy. Maybe we can develop, but apparently this is not what the country decided. And for developing this technology, we really need to have all the, I personally believe we really need to have all the criteria really well defined, because okay, it's less worse than developing oil and gas, but if there is an accident, it can also be like pretty bad. And there's also like the social aspect that even sometimes here in Europe, although the people, they really let's say like to have a greener life, people that works close to those projects, they might not like it, you know. And we always need to remember that in the case of Brazil, if we see the map, uh it is, oh, sorry, it is not this map, unfortunately, it is very small. It's not close to big centers, and sometimes it's not even like close to places that we might have a very strong industry. So we need to remember that those people, they are very simple. They might not even know what is like a wind turbine if they have never seen it. So you really need to explain it. You really need to point things, and you need to know how to negotiate it. One of the thing is, okay, like depending on where you are, uh, it might be a little bit more easy to convince people, but we don't know. Maybe in those cases, you see, the competition is also like really, really big. Even the developers, they might have problems, and it's not only a problem with the society. Even the other stakeholders, like the oil and gas industry, they might feel, oh, this is not interesting to develop here. Like in the south, we have some coal power plants, which is something that's very different from the rest of Brazil. And you see, the south is the place that we might have more projects. Are those stakeholders of the coil being happy? Will they try like to stop the progress? This might happen. This is the thing. We will only have a certain when we have the regulation, and when we see like all together work for the government. And one of the things that is kind of hard is because this area involves so many, let's say, agencies, and the agencies sometimes they don't talk to each other. You see, like for the maritime spatial planning, this is something vital to the to to the Brazil economy, to develop everything in the sea. And this is something that sometimes involves even more agencies than offshore wind. But this is something that it's about to happen for so many years. They should have started this. I think the first pilot maritime spatial planning last year, but they don't have a forecast for this. And this is bad. Maybe this might also like impact, because the thing is, we don't have even though sometimes we will have the auctions, sometimes the developers, they don't have the data of this area. So let's say we do some early studies, but we also need to do some more detailed studies. There are this happens actually in the whole world. There are things that you might only found out when you're really building the project, you know. Sometimes, I don't know, you didn't do your let's say technical due diligence very well before building the project, so now you're like in the construction phase, and you might know that that area is actually not feasible to develop a project. Like the soil has problems. For offshore wind, there's also a thing called slope that you need to take into consideration, or areas that you have problems that you're going to install monopiles, and they will sink, you know, which is happening in a project in Asia. And this is a huge disaster. I've heard about a project, this was actually on onshore wind, that they were building the project on archaeological space. So this is sometimes a problem in the industry. Of course, we try to do all the simulations to gather the data, but unfortunately, sometimes might happen this surprise factor.
We have someone that wants to talk, but I will ask another question. You said a lot of the oil and gas companies, and here in Brazil we see that in this offshore. Who is leading the offshore development or that lead the studies are the oil and gas companies. And sometimes I look this and I think a lot, and I don't know if this is. I want to know this your opinion about this, that the oil and gas companies leading the studies and the regulations and something like that for Brazilian not Brazilian market, but the start of the offshore here in Brazil, at least.
Yes, this is a good question. This is a kind of a political situation, because sometimes who is trying to lead those discussions are the people that they might have some influence in the political fields as well. That doesn't mean that maybe they're more skilled to develop a project. As working as a consultant, I did a project, a very early phase project, a site selection. That's the example that I'm going to show you guys now. This is our exercise. And while I was doing this site selection, uh, we were working in a huge team with lots of experts from the environmental area for other countries, and sometimes we only had, let's say, two guesses about some of the areas. Either the company only did a drawing randomly in the map. Maybe they consider the the wind resource, and that was it, or they didn't have access to the data that we had, you know. And unfortunately, I tend to believe that sometimes they didn't do like let's say, the basics before moving with with the project, I actually heard once for a potential client, and the potential client, we were talking about doing a project, and he told me, oh, maybe we're going like to only draw something in the map and that's it. So fortunately, this might happen. So, okay, maybe we have some people that they have some skill because they worked in the offshore wind market abroad, but there are some companies that they are it's a really new market, we might have some companies like Orsted or Vattenfall that they really have the expertise because they already developed some projects. But if they enter to a new market, they might also have problems. And even some of the local players, they don't have the skill. And this is I think this is the most critic thing of having like new skilled people. And this brings, I believe, a very good opportunity for people who really likes challenge and who really wants to work in this area. Because even here, I'm working in Europe, and I see some projects in a very well-developed market, and sometimes we cannot believe of the mistakes that they are going on. Are the people not very well capacitated? Because it is okay, sometimes it's a very small market, but we need resources, we need more people. And unfortunately, because we need people, we might not hire the most skilled people. And also, I have a colleague that she told me that even for we have lots of quality issues sometimes in projects, because the teams of a company, they cannot communicate themselves. So it's a little hard to integrate all the knowledge, even in a very well developed market. And this is a good opportunity for the markets that they are starting now, because you can you have the opportunity to not make the same mistakes that they have done previously in those projects, and maybe they are still making. Like, sometimes it might seem that it's only luck that the things they are running correctly, because of those uncertainties. This is, let's say, the real engineering uh, work. So we need maybe people to start changing this, because this is the thing that might lead to the decrease of the prices, working in a way to make those projects more accurate, and then this might decrease the insurance rates because we will have less incidents in the industry at um, in general. Yes,
Thanks.
Paulo?
Okay.
Okay, I can
Can
hear
I hear?
you.
Okay. Thank you, Ingrid. Just a quick introduction. And starting from the end of what you said to the beginning, I fully agree that we need specialized people and more specialized people dealing with this so new subject in order to be able to put it back on the trail. So I am part of this group. I'm back at UFMG here, performing a specialization course. I am an electrical engineering background and trying to get more professional knowledge on this. So my question to you is related to what you presented. I could see that back in 1991, 30 years ago, in Denmark, the first wind farm was there. So the beginning of the question is, did they have regulations by that time? And did they somehow evolve from during the past 3 decades? And number two is if the regulations in Denmark are, let's say, essentially the same as in other countries in Europe. Okay, so how all those things were put together.
Okay. Uh, let's say, I don't know. I cannot answer how was the regulation back then, but I actually can drop here a very interesting thing that I found out when I was talking to an engineer that he used to work here in Europe. Although we have some, let's say, guidelines for the offshore oil and gas industry, that let's say standards actually, that they are like really, really old. I believe that for offshore wind, the first one was a standard developed from DNV from the 2000s. And this is the cool thing about talking to someone of the sector, because this person told me that he works as an engineer, I think, as a structural engineer, uh, like finite models. And he told me that he had to work in a solution to solve some structural problem, because what happened when they developed this project that he was working on, we only had the regulation for oil and gas. So the project was developed according those standards. And when we see the technology, we know like the center of mass, the center of gravity of an offshore wind turbine is different than a oil and gas platform. And so they had started having some very structural problems. I don't remember what was the solution, but I remember this story because of this. Like, we really have huge problems in the in the offshore wind sector, and same as for the onshore as well. But in the offshore, there is a project that was this project was decommissioned, and Vinderby was decommissioned because it was like reaching the design life, and also maybe it could operate for a few more years. But I remember that there was also one, I think in Denmark, that they had to decommission it because one of the turbines failed, and the others they had a very high risk to happen the same, you know. So things for those first projects, they were kind of experimental, you know, and even sometimes for the floating. Now I think this is the time for the floating. Like we have this floating wind farm in Scotland, but we don't know how the things will turn at the end. I know that the prototype of the steam turbine from Equinor in Norway, apparently it's still running, you know, and the best laboratory to test the technology is on site. But Paula, I would say that okay, probably when they started, let's say it was a kind of like an R&D idea, and then they had to achieve the regulation, and now they have a regulation. Although like Denmark has been developing projects for offshore wind for like 30 years, I believe only in the last 5 years that they had subsidy-free auctions, you know, because they really wanted to invest in the technology. But this is a very interesting thing here in Europe, that here in Europe we have lots of subsidies for renewables, because maybe it's a cost that we can afford. And in Brazil, we used to have a similar mechanism. I don't know if all of you here know that we had a program to develop wind and solar energy. And due to this program, due to those subsides, we now have very competitive prices. So this could be like an option, but apparently the government doesn't want to do this because they think that they might equilibrate. They are not completely wrong, because when we are talking about the regulated market for for energy in Brazil, we have like the auctions for sources. And I believe that there was a study that actually the energy generated through waste is higher than offshore wind. Of course, if we're talking offshore wind in Northeast, that the resources are better, but are they doing the correct math? I don't know, because the supply chain there is very good for wind energy, but I don't know if they have like the best way of developing the foundations, this naval part, that this is an advantage that we have in the Southeast, or even in the South, because there's a very big construction yard in the South that was dedicated to some oil platforms. But in the Southeast, definitely we have this. But in the Southeast, I believe we only have like one wind energy project, which is very, very small.
Thanks, Ingrid.
I have a question to you, Ingrid. Can you hear me?
Sure.
Hi, nice to meet you. My name is Cesar. Actually, I'm doing my doctorate at Federal University of Santa Catarina.
Mhm.
My thesis is about to detect faults in generator, permanent magnet generators. But I was studying another article these days, 2 times ago, and I have some questions. And how can we accomplish some requirements to bring such technologies to Brazil? I'm talking about the vessels. Huh? We have special ships to transport and install some superstructures or substructures on wind turbines. Huh? So how can we bring such vessels, such specific vessels, to realize such transportation and installation in Brazil?
Yes. Well, actually, those vessels, well, this is a huge problem to the industry, because we have so many issues related to the workforce and also the supply chain. Because, okay, the companies, I don't know if we have like more than three. At least we have three very famous ones: Boskalis, Yandenu, and there's also Deme. Maybe we have another company as well, but right now I can only think on three. And all of those vessels, they sometimes it might be a little bit adapted from other vessels of the oil and gas industry, or they're building brand news, but it takes time. And well, it's a huge waiting line, because we have so many projects in Asia and in Europe and now even in the US, that those in the, I don't know if you know, in the oil and gas industry, all of the prices they are in in dollars, and you rent those vessels to do the installation. And the same thing happens here. So imagine, for instance, a project that's been delayed, because this happens a lot. Maybe you don't have like a license. Maybe a part of the, I don't know, the turbine or the foundation is not ready. You're going to delay the project, and they charge for a day. And we have to have into consideration that there are only like few limited vessels. I actually don't know what's the number, but I guess that we might not have more than 20, and for making the installation, it will take like at least one day, to do the installation of an offshore wind turbine. Of course, now things are getting sometimes a little bit faster, but uh, we have all those problems in the industry that might also impact this installation phase. And we might also have some problems during the installation phase, which delays even more the project.
Okay, thank you, Ingrid.
Anytime. So any other question? Let me see if I can send a message to Sarah. I don't know if I can call Sarah for her to open the breakout rooms.
I remember she said you could call her using the chat.
Yeah, but I'm trying to send her a message in the chat if we don't find any matches. Because I think because I'm an outsider from the company, from her institution. I'll drop her like an email asking her to
Don't you
come
have
back.
contact by WhatsApp?
Yeah. No. I'm actually now trying to use less WhatsApp.
Selfie.
But it's not a problem if we do like this exercise all together. But guys, do you have any questions? I promise I'll send the correct version of the presentation. I don't know why it didn't synchronize.
Sarah has raised hand.
Okay. They are not unknown. Stop the presentation. And then I'll go back again. So I don't know who raised the hand. The unknown, because it's appearing as an unknown user.
For me, it appears that just Sarah Matuelo has raised the hand. I'm not sure she's hearing us now.
Okay. But actually, if you like click on the raise hand, oh, Sarah's back.
I think he or she is trying to talk, but we
Might
cannot
be
Hello.
hear.
mute.
I'm here now. Can you hear me?
Yeah, sure.
So
Can
what do you
hear
want me
you.
to do? You want me to make rooms?
Yes.
How many? I mean, I can basically say how many rooms, and I can do it randomly that people get assigned in random groups. But you just have to tell me how many you want. Like,
Let me
I mean,
see. We have 33. Maybe if we divide people like in 6 rooms.
I think there's more than 33 because there's 33 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think there's more like 40.
Okay, because it's
I
appearing
do
only
6.
31 in the meeting for me.
No, yeah, I see 31, but I think that's 31 plus the people. I can see a load of people, and then I can see 31 other people, and I think it's 31 plus.
Okay.
Anyway, it doesn't matter. But
Okay.
I think if you have like maximum 6, if you have 5 people per group, I think I better do 7 groups or 8. Don't know.
Okay, that works.
Whatever. Sometimes it takes a bit of time. Sometimes it just takes a bit of time. So I'm
But I don't know if it will be possible for them to see the exercise during the.
Yeah, you have to go into each room and send it them, or you have to give them a link, or you have to go into the room and show them something. So I can do seven groups times 4. So when I press open, it's going to start putting people in, and it takes a few minutes until it works. But Ingrid, you're going to be assigned one of the rooms, so because I'm doing it, not you. So you have to then leave the room again, and then you can go in any other room. Hopefully.
Okay.
Let's see what happens. I'll stay here. You come back out of the room, and then we can talk to each other. I'm going to press open now. It's going to show everybody in the rooms.
Okay, I'll see if I can send a screenshot in the chat.
I'll just send a link if you've got a shared document.
Yes, it is actually. But I don't want to spoil the surprise, because there's actually.
Did you not get in any rooms?
Tivemos que nos adaptar de uma hora para outra. Pelo que entendi, iam ser 4, né, por sala, né? Então nós 3 aqui.
Ai, caramba, sem querer.
Oi, pessoal, bom dia. Eu perdi a conexão que ela estava falando ou realmente já dividiram os grupos? Não sei se foi meu computador.
Acho que ela está organizando ainda as salas.
Ah, sim. Obrigada.
Eu não sei como é que vai funcionar isso, não. Então, talvez ficar aguardando aí.
Já eu fiquei na dúvida se foi o meu computador que perdeu a conexão.
Parece que está mudo dentro do link que ela está tentando criar.
horas. Hello, Sérgio. I can't hear you. Okay.
Oi. Oi. Nós estamos na sala errada, a gente estava numa outra sala há pouco.
Não, eu voltei para a principal aqui para tentar saber o que a gente tem que fazer.
Não, eu tinha sido levado para uma sala onde estavam já...
Um instante, gente, eu estou com 2 microfones abertos, então tem 2 pessoas tentando falar comigo. Deixa eu fechar um instantinho o Anderson, tá? Para falar com o Sérgio.
Não, estou ouvindo você perfeitamente bem.
Sim.
Eu estava numa outra sala lá com o nosso grupo.
Tá, a gente foi lançado em salas separadas, tá? Por isso eu voltei aqui pelo navegador para essa sala principal, mas estou precisando descobrir o que a gente tem que fazer.
Pessoal,
Oi.
bom dia aí. A Sara acabou de colocar no chat aí um link,
O que fazer?
né? É um link que ele vai te direcionar, vai nos direcionar para uma questão, né? Então, assim, foi dividido em grupos exatamente para... porque é algo de discutir, né? Então, acaba que eu acho que como ficou meio as salas, o pessoal acabou voltando para a sala principal, aí a ideia é uma questão para discussão, né? Que está colocado aí no chat para vocês o link, e aí que nessas salas, nessas subsalas,
então.
haja a discussão.
Tá, tô indo lá então. Obrigada.
Oi, eu não tenho aqui.
No chat, você tá vendo o chat?
Eu estou vendo o chat aqui, mas no chat não tem nada.
Deixa eu colocar aqui novamente. Coloquei agora um drive. Veja se você conseguiu chegar.
Opa, está lá ele ali. Vamos lá, Vitor.
Vitor, bom dia. Você me ouve, Paulo?
Estou te escutando.
Na verdade, eu acabei ficando em 2 aqui. Eu fui redirecionado para uma sala que está meio silenciosa e, ao tentar entrar de novo, eu caí aqui. Eu já tenho o link no chat dessa outra sala e já vi lá uma questão colocada pela Ingrid. É isso?
É isso mesmo, sim. Eu tô presumindo que é isso, tá, pessoal? Eu tô como espectador aqui também.
E a discussão seria nessas salas individualizadas.
Exatamente. Eu acho que é a ideia.
Tá. Ok. Vou voltar lá na outra e vamos ver se ela toma vida.
Pois é, eu não consigo voltar para outra lá.
A outra, na verdade, eu não saí dela. Eu me mantive nela quando eu recebi o link e, como estava muda, eu me conectei de novo no site principal e caí aqui com vocês. Foi o que aconteceu, tá?
Também tem a mesma situação do professor Paulo também.
Então, eu não cortei a primeira, não.
Vamos ver se eu consigo ingressar. Não, eu agora encontro um problema ali, não entro mais mesmo. Eu estava em outro computador, né? Só que eu não tinha. Eu perdi minha câmera, né? E fui perdendo ali as coisas todas. Aí saí para voltar e quando voltei, puf, né? Aí morri em geral. Né? Deixa eu ver com meus colegas aqui como é que eu entro lá. Tá? Obrigadinho.
Structure.
Opa, tem algo acontecendo aqui agora.
Agora foi embora. Oi, Sérgio.
Agora eu estou aqui.
Opa, bom dia. Bom dia.
Oi, bom dia.
Bom dia.
Estava me sentindo abandonado aqui, não conseguia falar no outro, saí, sumi. Eu digo, cara, eu odeio esse troço aqui, pelo amor de Deus.
O idioma do workshop voltou a ser o nosso querido português, foi isso? Que maravilha.
Ah, mas eu também falo português. Ultimamente não muito.
Todo mundo no mesmo
Dá um
time
minuto lá
aqui.
no carro, tira no banco de trás, tem uma multímetro.
Rio Grande do Sul.
Só o portal
Does anyone except Sarah speaks another language besides Portuguese?
Well, people, Sarah is on the room now. So let's talk something that she understands.
Oh, hello, Sarah.
Sarah's mute.
I can hardly hear anything anybody's saying apart from the fact that you're all speaking Portuguese, except for me.
Now we can turn back to English.
But Sarah, you live in Europe. It's normal to hear even Portuguese. Actually, here in Hamburg, I can sometimes I hear some Portuguese, and it's very, very strange.
We are everywhere.
You can speak Portuguese.
Portuguese are everywhere.
You can speak Portuguese for the next 15 minutes without me if you want. I'm going to go away and come back in 15 minutes. What you do if everyone else is Portuguese speaking, then it doesn't really make sense to speak English. But there are some people registered for the course who are not Portuguese speaking, actually. So maybe you do want to do it in English because maybe there isn't. I don't know. Maybe not everyone can speak Portuguese.
Yeah, actually, we're speaking in English, so even when I was in the breakout rooms.
Oh, okay. Well, there you go.
In my
doing English.
It's a good way to practice. I think everybody's back, right?
Yes.
So, I can share my screen. Fortunately, I won't be able again to see you guys, but this is the question. So I invented a company that they want to develop now some offshore wind projects in Brazil, and they hired you to advise them in which aspects they take into consideration. And I don't know if you had any ideas about it. There might be not a wrong answer, but the thing is, I was talking to Amanda in our breakout room, and it's actually a very complex. If you do the site selection really well, it's a very complex analysis. So I would like to hear which aspects would you consider to do a site selection?
Okay.
I think that the opportunities for the discussions in the break rooms, at least in my case, it did not happen. Okay, I think we were quite silent and waiting for something. So what I'm going to say here is based on what I heard from you today. Okay, no previous experience on wind energy or industry, but I think, as you said, it is a complex subject. Many things need to be checked, such as Navy restrictions, environmental restrictions, closed cities restrictions, so many companies, so many institutions and organizations involved here in Brazil. I don't know exactly which they are, IBAMA, Navy, or whatever. If there is no gas for harbor construction on that area, and things like this. Okay, we need. I think that the important conclusion that we need specialists with experience on this to be involved on this analysis. Okay.
Yeah, I think that that was actually like a good analysis to do like in 12 minutes, because the thing is, okay, like I talked about the restrictions, but I didn't told much about them, because we might have like the restriction according like to the costs of the project. So and of course no place will be perfect, as I was kind of talking to Amanda, because okay, the first thing of course we need to have a look is the wind resource, and I think this is something that everybody here will agree. But it's not only about that, because you also need to analyze this resource, if it's like high enough, if the turbine that you're choosing, that you plan to use in your project, has like the best efficiency, and also like the wind direction. Because one of the thing is, if you're building in the northeast is one thing, but if you're building in the south, the wind profile is different because it's not that uniform as it is in northeast. But in the northeast, as I said, like we have the industries there, so they can provide the turbine itself. But in the northeast, we have a huge problem. We have like the tourist aspect, because everybody knows that the northeast is it's very known for the tourism, and also like the lack of infrastructure. We see now like the port of Peseng uh, wanting to invest in offshore wind or green hydrogen, but maybe we will need to build another port. And will the government contribute to that? Is that interesting? Because we have three ports in the Northeast. We have Peseng, we have one in Maranhão, but it's not close uh, for let's say economical aspects, like the distance for do like the repairments, to do the O&M, or even the port in Maranhão is more focused on mining, because they export the mining from the north to Europe or to Asia back then. And we also have the port of Suape in Pernambuco, but Pernambuco is far from the main region that they want to develop the project. So those are like all of the aspects that we need to take into consideration. Also the grid. The grid is very important because we need to remember that, okay, like the grid planning, we can only see for 5 years, and for developing a project, it might take, at least for the first ones, it might take, I don't know, 6 or 10 years. We always say, oh, the transmission line will reach the project. But that doesn't mean that you're going to be allowed to use one of the substations. Maybe you need to build one. And this might bring extra costs. There's also like the environmental aspect that we have like the protection zones. Some of them, they are like really, really strict. It is impossible to build even like an offshore wind farm close to them. And there are others that they are more flexible. But we also have like the endangered species that we need to do it. And the lack of data sometimes it's a little bit difficult, because it's something that maybe for the first aspect you need like to map, I don't know, like 10 different areas, and then you need to go deep. You need to start doing real service in that place, right? Even same as for the wind energy resource. So that's why this is a very complex. And there are also some aspects from the Navy, like UXO, that I actually don't know if this would be like a huge problem in Brazil, but I know that here in Europe, or for European companies, it is actually very well, let's say, it's a very crucial aspect. for offshore projects in general, not even offshore wind. And there's also maybe like some remaining substructure like shipwrecks that you might have, and the shipping lanes that you cannot like change. When we talk about like the southeast region, we know that the shipping flow there is more concentrated because we have like the transportation, the cargo transportation, but we also have like the oil production. And there are some areas that they might be like really feasible for offshore wind, but they also have oil. And in this case, what is more interesting to develop, you know? This also like includes the political aspect. Are they already like going in the rounds, in the concession rounds, or in the sharing rounds for production or not? So that's why this is a very complex topic. I included some aspects in the next slide that I was very I should have showed you this because this might also give you better ideas. And after today, I will include more aspects to you to like show a little bit more of what we need to take into consideration.
Yes, there is one point that well, that I'd like to consider too. If you are looking at this region, there is a very huge site that's being licensed at the IBAMA, the environmental
agency
authorities here in Brazil. And if you take a look of our geography, you see there are two rivers, and the mouth of this Patos Laguna is the river Mampituba in the north and Tramandaí. And these are regions where fisher have their bases. So the potential here in the south is very big, very big. And you have both relatively shallow waters because you have kind of a plain leaving directly in the shore. And then you have that big levee that goes down to 500, 700 meters, about 100 meters, from 50 meters to 100 meters from the coast. And so you have two different scenarios for placing for placing the turbines. But there are fishing boats working there, and that would impact the economy impact would also impact, well, the environment impact would also impact the economy of those regions, of those communities. I think always on all the beaches you see fishing boats traveling away, and this is for me always a good question, because you have to consider the environment, but you have to consider also the economy for these populations and for these towns that live, well, part of their economy is from that. This is a very important consideration to take.
Yes, it's a very important point. And let's say to mitigate this problem, there might be some mitigation measures that a project might have. One is to pay a compensation. Another possible solution would be to develop an aquaculture farm. It could also be like in some area of the park. Of course, like when we talk about developing an offshore wind farm, sometimes it might also have like a change in in the fauna close by, because we will start having some let's say some things are going to start growing in the structure, and this might attract fishes and other animals. So the fishers, they will want to go to this place to fish. People that works in the oil and gas industry say that this sometimes happens, and it's a small structure compared to an area of an offshore wind farm, but this can be also like a solution to put the to include those aquaculture spaces close to the wind farm, or in an area on the wind farm, and also like to educate the population that works there. You need like to train them to also be part of that project, because sometimes the fisherman that he works there, he might know something about the waves. He can work in the repairment, and maybe paying the compensation is not enough. You also need to change the life of the person. So there are like lots of ways to deal with that, but this is something that the stakeholders, the developers, they need to do this job, because otherwise, like, the community won't accept.
Is it a good time to stop this session? Have you come to the end? Has everybody presented? Because it's about to be 3:00. Maybe people want a couple-minute break before I start talking at them for an hour.
But if someone wants to drop a question, I'm okay. We can do a break, but it can be like an optional break.
Yeah. It's just I've got a hard stop in 2 hours from now. So, why don't we do a 5-minute break, and people who want to keep talking can keep talking for 5 minutes, and everyone else can quickly go and get some coffee or.
I also need to go back to work, but I can wait.
You need to,
5 minutes.
No, you don't need to be in my session though. So I'll start talking at 15:05, and everyone else can do what they want in the between time. But yeah, sounds like you had some good discussions. All right, see you in 5 minutes.
That's good. Thanks, Ingrid. I'll take the 5 minutes break.
Okay.
Thank you, Ingrid. Congratulations for your presentation.
Thank you.
Thank
you
you,
guys
Ingrid.
will have access
Thank
to
you
a
very
better
much,
presentation.
Thank you, Ingrid. We'll be back in 5 minutes. In how much time?
Yeah, until
5 minutes. We have to take a break.
Yeah.
Okay.
And then the session will last until 1.
Okay.
Yeah, I think you need to keep in the. But I'll wait for the 5 minutes here in case anyone wants to ask something.
Okay, I'll be back in 5 minutes. See you. Thank you.
Is everything okay then, Ingrid? Are you everything?
Yes, nobody dropped any question in this break.
Okay, they had to work. They earned their break probably. Are you putting any information on in the shared folder?
Yes, I put the presentation, but I don't know, like it was finished, but it wasn't updated. I don't know if I have some synchronization problem, but then I will update it again in case it missed.
You know, in the folder that we have, there's a subfolder called shared, which you could copy your final version into. It's not the same folder.
Ah, okay.
I'll show you quickly just while everyone else is taking a break. Do you see my folder structure?
Mm-hmm.
You know, this is the folder where like all our lectures are in, where you probably got your lecture from just now. But I created a subfolder called shared, which is the link that I've shared with all the participants. And that's the place to put things in that you definitely want to share. So this one, at the moment, these ones are not shared with participants. So if you want to share the final version of your presentation.
Yeah, sure. I will also include the resolution or some aspects.
Yeah, exactly.
And one of the things that I will think it would be really nice is that I included some links that I also showed in the presentation, but there is a very interesting document for offshore wind energy. And well, I think if everyone reads, or at least some of our attendees, they might ask lots of questions for us, not only for Brazil, but even for the world, like workforce and resources and land use.
Yeah. That document you want to put in the folder as well, or?
Yeah, I can include the report. There's also like the link in my references, but we can put separately saying important. Read this by Friday. Have fun.
Yeah, if you haven't got anything better to do. Okay, I'm going to start with my part now. So yeah, thank you from my side as well, Ingrid, for your time and lecture and participation. And we'll see you on Friday then for the panel discussion. Yeah.
Yeah, naturally.
Naturally. All right. See you later then.
Tschüss.
Okay, so everybody happy? Any questions before I get started?
Just a quick question, Sarah. This is Paulo here. So you're going to get a link to access the presentation from Ingrid sometime during the week, right?
Yeah, I mean, I put a link in the chat already for the shared folder, which you all have, which you can all access. We can put it in again because for the people who joined later, I think they might not have seen it. So the link's in the chat, and that's got.
Okay, good.
It doesn't have anything in it at the moment, but I'm going to put my lecture in it after today, and other people. Ingrid will put her lecture in, or I'll put her lecture in there tonight or tomorrow as well.
Okay, good. So that's the link. Thanks.
Yeah. All right. So I'm going to start my lecture now. So I'm not really quite sure of the background of you all. I mean, obviously you're all a big, diverse group of people, and I think quite a few of you are students. So my lecture today is quite a basic one. So what are the first things you need to know technically about wind turbines if you want to work in the wind industry? The next lectures on Tuesday, Wednesday, Thursday, Friday go into some of these things in much more detail. So my goal is just to give you quite a rough overview. And then in the second part, we're going to do an exercise. So if you have Excel available, or you can do it in MATLAB or any programming, but I'm doing it in Excel. So if all of you have got Excel available, the exercise will just be doing some basic calculations. So first of all, I'm going to talk just generally about how wind turbines work. I'm going to tell you a few about different concepts, and then we're going to talk about power and energy, which are very important for wind energy. And then at the end, we have the exercise. Feel free, by the way, I can see the chat, so feel free to type or just turn your microphone on and speak to me. It's kind of weird doing an online lecture and just talking to my computer all the time. So the more questions or comments, the better, so that I at least know that you're still awake and paying attention. So just, this is like a really general diagram, basic, that to show that wind turbines generally work by, they take energy out of the wind, right? So you imagine the wind is coming from the left onto this wind turbine and it's rotating. Why it rotates and how it rotates is a different topic. We'll get to that tomorrow. But somehow the blades produce lift, and that leads to the rotor rotating. And it's called a horizontal axis wind turbine because the axis of rotation is horizontal. And somehow this wind turbine converts some of the energy to electrical energy, but it doesn't convert all of it, right? So it's going to be impossible for us to convert all the energy in this wind to electrical energy. And so some of the energy keeps going in the wind behind the wind turbine, but you just have less energy behind. So this area behind the wind turbine is the wake, and you'll have a lecture about wakes on Thursday. But generally you have less energy in the wake because you're taking energy away. You do actually have some rotational energy added, but the main energy, I mean, you get loss basically behind the wind turbine. So the total energy in the wind is a sum of the energy that you have behind the turbine plus the electrical energy which you take out. And you may have seen some different types of horizontal axis wind turbine before. The most common one is just this three-bladed. There are some strange designs as well, where people try to build a large number of blades. We'll talk about the number of blades as well later. In northern Germany, there are some two-bladed wind turbines as well. We'll talk about that. And then this is kind of what the components look like in a wind turbine. If anyone's been into a wind turbine, you'll know that it doesn't look anything like this picture here at all. It actually looks like a very big room with these very big components inside. Usually you can stand up inside here. So you have the blades and the hub, which is this bit at the front, which make up the rotor, the rotational part, and that's attached to the shaft. You have a bearing as well, which is holding the shaft but letting it rotate. And then usually you have a gearbox, which speeds up the rotation because the rotation is much slower than the mains frequency that the generator needs. We'll talk about that a little bit later. And at the end of the day, you're then putting this electricity, which is created in this generator, then into the grid. You have the nacelle, which is basically the big box around everything. And then you have the tower. And then at the bottom, you have the foundation. Wind turbines work that they line up with the wind. So you're rotating this bit here is the whole top is rotating and lining up with the wind, depending on the wind direction. So you also have a large motor and bearing at the top of the tower, which is marked on the picture here on the right. That's called a yaw motor. Some important things to know about wind energy. So one thing is that the power available in the wind is proportional to the cube of the wind speed, and it's proportional to the area of that the blades cover. The reason why this is so important is because it basically means you need high wind speeds if you want to get a decent amount of power production, but you also need to be as big as possible. One of the mistakes that people make, for example, where I am in Switzerland, there's many urban regions which have low wind speeds. So people, they want to install small wind turbines. And I try to explain to them with this equation, if you're in an area where you have low wind speed, you're going to be really, the power available is going to be tiny. Therefore, you need a big area. If you have low wind speed, you need a really, really big wind turbine. So small wind turbines only really work if you have very high wind speeds. And the R is the air density. And but we don't, as you know, as we said, we don't take the entire power from the wind into electricity. We convert a certain proportion, and the proportion that we convert is known as the power coefficient, which is just the power of the wind turbine divided by the power available in the wind. That has a physical maximum of 60% or 59%, which is called the Betz limit, which we'll talk about later, but also in the lecture tomorrow. If you just plot this equation, P is half rho V cubed A. We have power on the y-axis and wind speed on the x. You just get this big exponential curve. And if you just multiply that by CP, which is maximum 0.6, but usually a bit lower, you then get a second curve. And these curves we're going to use later. And then the next important thing to know is that the wind speed is increasing with the height above the ground. So this is just showing the wind speed on the x-axis and the height above the ground on the y-axis. And there's usually some sort of profile that looks a bit like this. And this is called the atmospheric boundary layer. And it could go from 200 meters, it could be 200 meters thick, or it could be a kilometer thick. It's very dependent upon the surface covering, and so on the area where you are in the world. But this has a significance for wind energy, because first of all, it means you just want to build as high as possible so you get a high wind speed. But it also means that you want to choose an area where this profile is rather flat, because if it's a steep profile, it means that if you imagine the blades turning, the blade at the bottom is going to see a much lower wind speed than the one at the top, which is then going to lead to a high dynamic loading, which then leads to more fatigue. So for example, offshore, you have a much steeper profile, which is one of the attractive things about offshore as well, apart from the fact that the wind speeds are just generally very high. Just about the wind quickly. So I don't know if you know, but the wind comes from the sun actually. So the sun heats the Earth's surface differently depending on the land cover. So desert, forest, mountains, or sea, and depending on the time of day. And you get differences in air temperature, and then you get convection, which is just air of different temperatures moving around. You also have the rotation of the Earth, which creates these Coriolis forces, and it just leads to a very complicated global wind system. And which, if you have a wind turbine, the wind turbine's experiencing all these changes. So the wind's changing with height above the ground and with altitude. Generally, it's changing with direction, and it's changing with time. So I've got a little diagram here sort of showing these changes. So the top left picture is just showing, imagine you have a wind measurement device in the wind, and you're just recording the wind speed every second. It kind of goes up and down, and you can take an average over a day or a week or a year. And if you, on the top right, we're then showing a frequency distribution. So a frequency distribution is you're adding how often you get each wind speed. So you may know, for example, that the height of people in Europe follows a normal distribution, right? Which means if you count how many people weigh 50 to 55 kilograms and how many from 55 to 60, and you divide it up into classes, you get this distribution where in the middle, where you have the mean, you have the most number of people, and then you have less people towards the edges. And the wind speed is similar. You can count how often you have wind at different speeds, and you can create a frequency distribution. And usually the wind speeds approximate a so-called Weibull distribution, which is similar to a normal distribution, but it's parameterized by two numbers. And this is very important. We use this a lot when we're trying to predict energy, which we're going to do in the exercise later. And then you have this vertical wind profile, which is what I was saying before, that it's the wind speed's changing with the height. Usually you do you do a power law approximation, which looks like this, which is just basically saying the wind speed at a certain height is the wind speed at a certain lower height multiplied by the difference in height to the power of alpha. And then alpha is a value which varies depending on location or various different things. And then turbulence is known as the standard deviation divided by the average. So that's basically just giving you a measure of the fluctuations. So if you imagine this picture on the top left, the bigger these fluctuations around the mean, the higher the turbulence. Turbulence is important in wind energy because of the fatigue loading, which you'll hear about tomorrow a lot. But actually, for the rotor blades, it's the defining factor. So wind turbine blades break through fatigue before they break through maximum force. And then the wind rose is showing the variation of wind speed with direction. This is important because, well, the wind turbine is moving to line up with the wind speed so that it can get the maximum amount of power out of the wind. But if you think of a wind farm which has got lots of wind turbines, and you want to avoid them having a large effect on each other, you know, if you put them too close to each other, they won't see as much wind. The wind speed they see will be lower, and the loading will be higher. So you want to distribute them so they don't affect each other too much. But the wind direction is very important for this, because if you, depending on the wind direction, the wakes of the wind turbines are going to be pointing in different directions. But Raphael will talk much more about that on Thursday. And then to the topic of different wind turbine concepts. Or can I maybe ask if there are any questions on that first part yet? So that was basically just a first introduction, a couple of important concepts in wind energy. Is there something about that that's not understandable or that needs clarifying before I continue?
No questions to me.
All right, thank you. Okay, so I'll continue to talk about a few different concepts. I'm going to go through all these different concepts now and comparing. So the first thing is about the number of blades, which I already mentioned. Maybe some of you know that the power of a rotating machine is equal to the rotational speed multiplied by the torque. So if you have for the same amount of power, if you have a high torque, you have a low rotational speed, and if you have a low torque, you have a high rotational speed. And this is important for this question about how many blades does a wind turbine have, because as you reduce the number of blades from left to right, you actually have to rotate faster in order to reach the optimal power production. And that's just to do with the fact that the less material you have, the quicker you have to go to have the same coverage of the area. And also because the blades interact with each other when you get lots of blades. And so if the number of blades reduces from left to right and the rotational speed increases, it basically means that to keep for the same amount of power, because of this equation, the torque decreases. And what we want when we're producing electricity is we want a high rotational speed, because we are, at the end of the day, we're putting our electricity into a grid which needs 50 hertz, or depending on what country you're in, something around 50 hertz, which is very high speed. Like a wind turbine actually with 3 blades, for example, rotates like one hertz or something, and so, or even half a hertz. So the slower you're rotating in the rotor, the bigger the gearbox needs to be. And the gearbox is a very sensitive, large, unreliable part of a wind turbine. So if you want to create electricity, you want to move fast, which means you actually want one blade. Now, does anybody know why we don't have one blade? Why do we have 3 rather than 1?
Vibration.
Yeah, so vibration, so asymmetrical loading. So if you just have one, you have this massive weight on the end going round and round. And if you imagine on the center of the wind turbine, you're experiencing these massive changing forces just due to the weight of the blade. And it's just going to break really quickly. And actually 3 is the optimal, because it's the it's the weight of the blades which is the main contributor to these forces, and they, if you think about the force going vertically down, they actually compensate for, like, they're symmetrical at all positions wherever the blades are. So that's one reason. Are there any other reasons that you know of or can think of?
I think about the opportunity of taking advantage of the difference of the wind everywhere. Because you have if you have only one blade, you may be passing this blade, have this blade going in a part of the movement in a place where there is wind, actually to move it, and the other not. So and when you have 2 or 3, you are always taking the opportunity of the wind distribution.
Yeah, I understand.
Does it make sense?
Yeah, the theory makes sense, but actually in practice, it's not one of the reasons, because I think the variation over the rotor is not large enough. Yeah. But it's a good idea.
Yes, the speed is high is okay.
Any other ideas?
Well, I would say it is a very ugly arrangement, isn't it?
So just from the way it looks.
Just one blade.
Yeah, I mean, some people think that the more blades there are, the better it looks, or the nicer, the more, the less it disturbs people. That's what some people think. That's not one of the top 3 reasons, but I do think it is a reason. Was somebody else speaking as well?
I think there is something about power coefficient. Because
there is some, yes.
Blades we have an optimal extraction.
There is something about power coefficient.
Not the best limits, not the best
limits.
But...
Yeah, you're right. So it's the optimal. You improve the power coefficient actually with more blades, but you it only increases from 1 to 2 to 3 to 4 to 5. The increase is decreasing, and so actually when you go from 3 to 4, you're only improving by 2%, but you're increasing the costs by 33% because you've got another blade. So that's one of the reasons. But the other reason is noise. So noise is the noise that you hear from a wind turbine blade. It increases with the tip speed to the power of 5 or 4 or 5. I'm not quite sure, but very high. And so the more you can reduce the speed, the better you can optimally design the performance for a certain amount of noise, right? So you basically reduce the noise to decent limits, and the noise just increases massively from 3 to 2 to 1 blade. So 3 is just the best compromise from that. And then there's constant and variable speed wind turbines. So like old-fashioned wind turbines used to have a constant rotational speed. And the problem with that is that the performance changes with wind speed, as I'm going to explain now. So you have this thing called tip speed ratio, which is the blade tip speed divided by the wind speed. And the blade tip speed is drawn here on the right. It's the radius multiplied by the rotational speed. And the value is usually between 5 to 8 in order to actually extract energy out of the wind. And the thing is now, what happens if you have a wind speed that's already, if you have a constant rotational speed, but your wind speed's varying, the tip speed's changing, right? And if you look on the left here, we haven't talked about this yet, but the power coefficient, which I mentioned, that has this maximum of 60%, it actually depends upon the tip speed ratio like this. So it's got a maximum. This is because of aerodynamic reasons, which you'll talk about tomorrow. But basically the design of the wind turbine can be optimized so that you're always in this area where you have the maximum power coefficient. But then now imagine that the wind speed's changing, but you have a constant speed rotation. You're going, every time the wind speed changes, you keep sliding down this curve and getting a lower performance, basically. And so what you do with a variable speed wind turbine is that you use a frequency converter in the generator to keep to alter the rotational speed, you measure the wind speed, you alter the rotational speed so that the tip speed ratio stays the same. So you stay on this maximum power coefficient, which is why large wind turbines are all variable speed. Does that make sense? Yes. And then there's this thing called upwind and downwind, which is not that commonly known, but most wind turbines are actually upwind wind turbines, which means that the rotor is upwind of the tower. If the wind speed's coming from left to right, the first thing that wind turbine sees is the rotor. But the problem is with that, well, one of the problems is that the blades might hit the tower. That's actually the deformation of the blade. It's actually one of the design conditions for a wind turbine as well. You can see that this picture is that the blades are kind of cone. They've got a cone. They're not straight, and that's actually to try to avoid that. But the other thing you can do is that you can turn the wind turbine around and have it actually operating this way, which means you avoid this tower being hit. But it's got, well, the other advantage is that you don't need an active yaw control. If you have the center of the aerodynamic center of this wind turbine, like behind the rotational axis, it actually means that it lines itself up with the wind. You can imagine that better with this picture, I think. This is a small wind turbine. If you imagine this large black area here, if the wind's pushing against there, it actually pushes and lines up the wind turbine by itself. And that was one of the reasons why some small wind turbines have this downwind construction, just to avoid having to have yaw control. But it's not great because you're going through the wake of the tower every rotation, and you're increasing the loading. But there are some companies actually looking at large scale downwind wind turbines because of these advantages. But the established technology is the upwind. And then stall and pitch control. I told you we were going to come back to this diagram. This is the power increasing with the cube of the wind speed, and the blue is the just that multiplied with the power coefficient. Now we need to limit the power of the wind turbine because wind speeds higher than around 12 meters per second don't happen very often. And so if you imagine if you had a generator that could deliver power at these high wind speeds, it doesn't warrant the extra costs, because imagine now I'm going to buy a wind turbine that's got an 8 megawatt generator. It's going to cost at least 4 times more than a 2 megawatt generator, even more. So I'm using the power here. But imagine I never have any wind above 12 meters per second because of my variable frequency distribution, and then so I'm paying 4 times more money, but I'm not getting any more electricity at all. And even if you have wind like a few days in a year, at those wind speeds, what you're gaining is much less than what you're paying extra. So there's some sort of compromise that has to be made between actually increasing the electricity production in the small amounts of time where you have high wind speeds and the extra costs. And so you're always going to end up having to protect the generator, because whatever size you choose, at some point you're going to have, at least for 1 minute a year, you're going to have wind speed above its rated power. And so you have to make the power, you're basically forcing the power curve off this pale blue line, you're forcing it down to this dark blue line. And the way you do that, so the old-fashioned way of doing that was called stall control. And so we'll look at the aerodynamics tomorrow, but the air flowing over the blade is creating the lift, which is creating the torque on the rotor. And this, in order to create lift, you have to have a smooth flow, like on an airplane going over the wing. And at some point, if the angle between the airflow and the blade becomes so high, you get this thing called flow separation, which just means that the flow is now separated from the blade, and it causes lift is not being produced anymore, and it's basically the lift forces are reduced. The aeroplanes can crash due to this, but a wind turbine then actually stops creating power. And this can actually be used in quite a clever way by designing the blade that once the wind speed gets to a certain value, like 12 meters per second, it's designed so that it then stalls, which means that the power is reduced. It's actually a really cool concept, but it's not very easy to control because this stall is very dependent upon like how dirty the blade is, or even the air density, which is then changing. So it's not great to control it. And so there's this thing called pitch control, which literally involves the blades with a motor in the base, and they get controlled. The angle gets controlled, and that is really easy. It's very accurate. So the control system knows what angle the blade's got to be set at a certain speed in order to basically reduce the performance of the wind turbine on purpose. And it's actually built to do that actively, so it can look to see if the power is too high. I mean, it's got a general rule which is based on the expected behavior, but then it can adjust in order to keep the power on the right value. And that's what most wind turbines have. But again, it's you have to have a motor, you have to have a control system. So old-fashioned or small wind turbines might not have that, because it is some effort. This is kind of showing here on the left. Sorry, the writing's in German, but this is kind of showing this idea of flow separation, where the flow of the blade comes attached from the blade and causes this area behind which is like got vortices in it, and it's not producing lift. Or some of you might be familiar with like the flow around the back of a car, where you have this area here where the flow is separated. And on the right, I'm showing the pitch control. So it's actually showing the velocity vectors in different conditions, because the velocity seen by the blade is a vector combination of the rotational speed and the wind. But you're going to talk about that in more detail tomorrow. Yeah, and then the gearbox. So we talked a little bit about the gearbox, and the fact that the generator's got to move much quicker, rotate much quicker than the rotor. So the transmission ratio of the gearbox is the generator speed divided by the rotor speed. And the generator speed is actually given by the mains frequency divided by the number of pole pairs. So in Europe, the mains frequency is 50 hertz, and the standard number of poles is 2 pairs, which makes 4. And then using that information, you can then work out what your transmission ratio should be. So wind turbine gearboxes have a constant transmission ratio. They don't have variable transmission. That's too complicated and expensive. So the change in rotational speed is done with the frequency converter, which I'm sure Victor will tell you about on Wednesday. And so you basically, it's not really quite accurate, this slide, anymore, because you have quite a few solutions between now. But the two extremes are that you either have a standard four-pole generator, which is cheap, combined with a very large, expensive, unreliable gearbox, or on the right-hand side, there's some designs where you don't have a gearbox, but instead you have a massive, very expensive, self-developed generator. So Enercon were the pioneers of this, who are a German company. But actually today, you tend, with the very, very big wind turbines, you tend to have a combination of both. So you have a medium gearbox and a medium generator, and you have somewhere between the two. So, but yeah, that's kind of the development. That's a picture of these crazy big generators made by Enercon. It's worth going to visit them in northern Germany just to see the size of those things. And then to the tower types, there's some different tower types. So tubular steel has been the most common. Reinforced concrete tower is also an option, and then lattice. And some of the reasons for the different choices. So tubular steel has been popular. It's very easy. It's just a big tube, and you can design it with low stiffness, leading to low costs. But actually above 80 meters or so, which the big turbines today are, reinforced concrete is becoming more popular again. And one of the reasons is also that you can transport them in pieces. And then lattice towers is actually, it's the easiest way of building stiff constructions, like the Eiffel Tower. And people use them quite a lot at the beginning of when wind turbines are first built, but people don't really like the way they look. And so there are some designs where people have covered, they've built a lattice tower, but they've covered it up with a thin cover so that you don't see the lattice. But I wouldn't be surprised if they came in more. Like, you know, the offshore structures, they're all, well, not all, but some of them are made like that as well. So it's a very efficient way to build. And then, yeah, so going on the topic of offshore, which is obviously important for you in Brazil, offshore is more complicated because you have to consider this whole support structure in the water as well. Then you've got all the logistics, which are much more difficult if you're trying to build these big things in the water. The reason that people go offshore is because of much higher wind speeds offshore, but also they're much more constant over time. But also this profile is steeper with the height, which makes the loading lower. I'm just going to quickly get a glass of water. I'm sorry, I'm getting a dry throat. I'll be back in 2 seconds. Okay, and then one of the disadvantages of offshore is just that you have to somehow design this big foundation or the support structure. And then you imagine the loading on the wind turbines. You have waves and wind, which you have to model, and they all interact with each other. And I think that's quite a big challenge as well. Then you have the marine environment. So you have the salt, and you have the humidity, and you have the animals living there. And then the whole topic of logistics is a big thing. Also, by the way, monitoring is difficult, right? You can't just send someone out very easily to look at what's happening to the wind turbines. The largest, yeah.
Hi. If there is a steeper wind profile, wouldn't there be more variation for the case of offshore?
No, because what I mean with steeper is, let me just do a quick drawing for you. I've actually got a touch screen, so I can draw on my screen, but I can only do it on the screen that I'm not sharing. So I'm just going to do a picture, and then I'll share it with you in a second. So it's just that the definition of steep is the opposite of what you think it is. So my definition of a steep wind profile would be the one on the left and not the one on the right. So if you steep means it goes like near the ground. So on the one on the left, the wind speed is on the x-axis and the height is on the y-axis. And so the wind speed is changing within a very small amount of time to a constant value, which means if you have a wind turbine up here, it sees a constant, like it's not steep here, it's flat here. Whereas a flat, a non-steep profile would mean that it takes a long time to get to the maximum, and then the wind turbine would be in that changing range. So it's just actually a definition of what steep means. Okay, it's just the other way around to what you were thinking, I think, probably. Does that answer your question?
Yeah, thanks.
Okay. Maybe I should reconsider if I actually call it steep. But yeah, anyway, okay. Yeah, and then this is it's not the biggest wind turbine in the world, but it's the biggest commercial. It's not the biggest power, but it's the biggest commercially available in terms of the rotor diameter and blade length. It's 10 megawatt rated power with 190 meters rotor diameter, 125 meters hub height. And there's also this prototype made by GE called a Haliade, which is 12 megawatts, and it's got a 220 meter rotor. I actually forgot to add, there's another one. There's actually a bigger prototype built by Vestas, now, which is like 15 megawatts. But actually, if you look at the dimensions, it's not actually bigger. They just put a bigger generator on it and pretended it was bigger. I mean, the blades are not bigger. Anyway, so I put some links in here. I'm going to share the slides with you, and you can see the links yourself, so you can get a feeling of how big these wind turbines are. Okay, and that was part 2. So I want to go to part 3, where I talk about power and energy, if there are no more questions.
Hey, Sarah, I have a question to you. I think there is a trend to use direct drive wind turbines.
Yeah.
And I would like to know how many poles are presented in those permanent magnet generators. Do you know this information?
Yeah. I mean, so 100%, I don't know 100%, but what I do know is that if you look at this equation, you can work it out actually. if you know, like, a transmission ratio of can be 50 to 100 depending on the size of the wind turbine. But if you did have a 1 to 50 transmission ratio, which you're basically replacing that with a direct drive, you need, instead of a 1 to 50 translation, you need to get that 1 to 50 translation in the generator. So you need 50 times 4 poles, right? So you need 200 poles. And I think even this 50 is kind of a low estimation, so it could even be 100. So I think it's somewhere between 200 and 400 poles. But I think that's a good question to ask Victor on Wednesday. I don't know exactly, but it's something around that. I mean, but they're crazy. They're massive things. I mean, these ones are actually not permanent. The Enercon ones are not permanent magnet ones. They're what's it called? I can't remember what it's called in English. Electrically, yeah. So, thank you. Yeah, electrically excited. Yeah. But there's these ring generators as well, which are the permanent magnet ones, and they're pretty ridiculously big. And there's also this question about the heavy metals getting used for that as well, which is not necessarily good. But that's what I'm saying. I think quite a lot of the current solutions have this hybrid thing where they, maybe not this one, but where they have a medium size. They do have a gearbox, but they kind of have a medium gearbox with a medium generator to kind of compensate. Like, it doesn't have a massive unreliable gearbox, but it also doesn't have a ridiculously heavy, massive 200 pole generator. It kind of compromises on both of them. But yeah, Victor, I'm sure will tell you more about that.
Okay. Thank you.
No problem. So moving on, I'm just trying to work out if I'm going to tell you all of this because we're kind of running out of time. I'm gonna just continue and talk about the job of the rotor. So the rotor is converting energy to rotational energy of the shaft, right? So it's the first thing that the wind sees, which makes it pretty important. And we've said before that the rotor actually wants to rotate as fast as possible to be efficient. So if you're designing the rotor, you need quite a lot of knowledge about the aerodynamics, but also about the structures. And then also the interaction with the entire system is important. When you're, for example, trying to avoid resonant frequencies, you need to know about the interactions. But you're going to hear more about that tomorrow. What I'm going to do is talk a little bit more at a global level. And so I know this might, for some of you, might be really basic, but it's really important in wind energy, and I'll explain why. So energy is traditionally, according to the standard units, is measured in joules, right? A joule is a watt second. But energy can also be measured in kilowatt hours, which is standard for electricity generation. And then a kilowatt hour is a kilowatt multiplied by an hour. So it's the same, it's just a different unit, but it's still energy. And the power in kilowatts is just the energy divided by the time. And actually the power produced by a wind turbine, the rated power of a wind turbine, is really not very important. What's important is how well the power curve of the wind speed matches to the wind conditions to get the optimal energy production. So the energy in a stream tube is given by just generally by the mass of the flow divided by 2 times the speed squared. That's just the kinetic energy law. And then because the power is the energy over time, this dot, if you're not familiar with it, just means variation with time. The power is the variation of the energy of time. And we also know from basic physics that the mass flow through mass flow of a certain volume of air or fluid is the density times the speed times the area. I'm not going to derive that, that's just how it is. And then if you put this m dot into these 2 equations above, you get that the power is m dot divided by 2 times v squared. And then therefore the power in the wind is rho divided by 2 times v cubed a. And that's basically why you have this formula I told you about before. And then you can derive this thing called the Betz limit, which is this maximum 60%, which I told you about. And we're not going to go over it in detail. Actually, I'm going to kind of skip over this. Let me just see what so I'm just going to tell you roughly how it's done. So if you apply continuity, which says that the mass flow rate stays constant through the wind turbine, and you apply the Bernoulli equation, which is a simplified version of the momentum equation around a wind turbine. I won't go into it now, but it's basically energy conservation of the air going through the wind turbine. And then you also apply the conservation of momentum, which says that the sum of the forces acting on a system add up to 0 linearly and angularly. You then consider this, imagine the flow going over a wind turbine, and you end up being able to derive some formulas from it. And I can share some links, I can share some documents where that derivation is actually done. I don't have time to do it really now, but basically, if you want to think about it, if you want to think about the air going into the wind turbine, it's expanding. And the reason it's expanding is because you're taking energy away. If you're taking energy away, it means that the wind speed is reducing. So in order to keep the mass flow the same, you have to increase the area, and then you get this wake behind. So if you think about the wind speed going over the rotor, you basically get this drop, and at some point it goes back up to the about 10 diameters behind. It goes back up to the free stream conditions. You have this thing called the axial induction factor, which is telling you how much. So it's what wind speed you have at the rotor compared to what you had at the beginning. So it's telling you how much you're taking out of the flow, basically. And then you get these results, which are some equations, which we won't go into now, but you basically find out that the power that you can extract relative to how much is available ends up being this equation, which is only dependent upon this induction factor. And the same with the thrust. So the thrust is just the force acting in the flow direction on the wind turbine. It's related just to the induction factor. So then you can plot this in a graph, and you see that the power coefficient and the thrust coefficient have a peak at a certain point. And so this is 0.6 is the peak in the power coefficient, and it happens at an induction factor of about 1/3, and that's basically the maximum amount of mechanical power that you can ever take from the wind if you had an ideal system, which you don't. So if anyone's interested in more details about that, let me know. I mean, I can put some stuff in the shared folder as well quite easily, because I lecture on that quite a lot. Actually, that value is 16 divided by 27, which is 0.59 something. The CT maximum is actually 1 at an induction factor of half. And then we've said before that this wind turbine is actually a rotating thing, and the aerodynamic forces, so the lift and the lift and the drag, which are created on the airfoil sections, they create torque in the direction of the rotation, and they create a thrust in the direction of the wind. And so that transfers to power of the wind turbine and also the loads acting on the tower. But the power coefficient is actually depending on sorry, it's not, I realize it's a bad translation from German. It's depending upon the tip speed ratio. You know, a few slides ago, we saw this graph, which is showing how the power coefficient has got this maximum depending on the tip speed ratio. And that's because of different aerodynamic and rotational losses that you get. This picture on the left is basically, sorry, it's in German, but it's showing this behavior. So it's showing the power coefficient against the tip speed ratio for different rotors, but all of them you can see have got a maximum at some point. And you can see the 3-bladed rotor usually has a maximum around 7, and the value is usually about 0.5. Yeah, and so what you can then sorry, about once an hour my internet connection breaks for about 5 seconds. Can you hear me now again?
Yes.
You can hear me properly?
Yes.
All right. Good. Sorry. So anyway, this power coefficient curve, when you buy a wind turbine, you basically get guaranteed 2 things. One thing is that this curve here is the power coefficient curve. So it's basically telling you, you know, you're going to have a power coefficient of 0.5 if you have a wind speed of 8 or 9 meters per second. But then it's translating that power coefficient into this power curve here, which is telling you how much power you expect at each wind speed. And yeah, when you buy a wind turbine, you basically get given these curves, and these curves you use to calculate the expected annual energy production, which is the next topic of the lecture, and also it's the last topic, and it's also the topic that we're going to do the exercise on. So if you want to save your attention, pay attention now. So the annual energy production is something that's pretty important for wind energy planning. If you're doing a site suitability study, so maybe you're looking on a wind atlas, if you are freely available on the internet, there are some wind atlases, there's some global atlases, and there's also some national ones, which roughly tell you what the frequency distribution is expected to be over a long time at certain locations. But it's not very highly resolved, but it's quite inaccurate. I'm sure Yoshi will tell you more about it as well in his lecture. But if you want to do a site suitability study, you know, maybe you're planning a project, you usually use these rough values to start with. But also then as a next step, if you've actually got some projects planned, you might want to do some first estimations of the rate of return, and then just generally understanding what the wind resource is like at a planned location. You need this value. And the annual energy production is energy, and it's measured in kilowatt hours per annum. So that's just, the A just means per year, annum per year. And yeah, I mean, it's just look at the units. So if you want to get kilowatt hours per year, you have to multiply kilowatts with the number of hours of the wind speed per year. It's actually quite simple. You're taking the power curve. So this is the power curve. We had this plot before where this power curve comes from. This is another example of a power curve that you get from a company. And this is, again, this is telling you if you have this certain wind speed, this is how much power you expect, but it's not telling you anything about the energy production. Like if you imagine you had a site which had 2 meters per second all the time, this wind turbine wouldn't do anything. And then so the second thing you need is this frequency distribution, which you can get from an atlas, like I mentioned, but you can also get it from a measurement on site, right? You get a met mast and you measure over, for example, you measure for a year, and then you have this frequency distribution. And then you can convert that to energy as follows, and this is the step that you're going to do in the exercise. So what you do is for each wind speed, you multiply, you say, okay, what's the power? So for example, at 10 meters per second, you expect 4 megawatts. You then multiply that by how often you have wind at that wind speed. So in this example, 4% of the time you have 10 meters per second. So you literally multiply 4% by 4 megawatts. You then multiply it by the total number of hours in a year, which is 365 times 24, approximately. And then for that wind speed, you see, okay, I have 1,423 kilowatt hours per year. And that's the energy yield for that 10 meters per second bin or class. And then you do the same thing for each wind speed bin, and then you can then plot the energy yield for each bin, and then you can add it up, and then you get the annual energy yield. And a few extra things to that, which you're also going to calculate. There's this thing called full load hours, which is usually used in other industries of electricity production. So full load hours is the number of hours per year the wind turbine would have to operate at rated power in order to produce that value. So you take the annual energy production that you've calculated and you just divide it by the rated power. And a typical value for a wind farm would be, a wind turbine would be 1,500 to 3,000. Well, actually, the big turbines are going to 4,000 now. And you can also turn that into a capacity factor, which might be something you've heard of. And actually, the capacity factor is just the annual energy yield compared to the theoretical maximum. But it's actually a really stupid definition, because the theoretical maximum is defined as, imagine this wind turbine was running at rated every single hour in the year. And we know that this is impossible. We know that the wind speed is changing all the time, and it's almost never, it's not very often at rated. And it's actually the full load hours divided by the hours in 1 year. So for example, you see this 3,000, if it was 4,000, you would know the capacity factor is roughly 50%, because you know there's like 8,000 something hours in a year. So in wind energy, it's usually 30, 40, up to maximum 50%. And it's really important to know that, I said before, this is kind of stupid. It's not a good idea to compare the capacity factor of a wind farm with a traditional power plant, because a traditional power plant is either on or off. Its capacity factor is like 90%, because sometimes it's being repaired, but otherwise it's running at maximum. So if you compare a traditional power plant with a wind farms always look bad. And I've heard people tell me, wind is bad because the capacity factor is low. And it just doesn't make any sense at all. Like, it doesn't mean it's bad, because the wind is not blowing at 12 meters per second all the time. It doesn't mean that it's bad. So you have to be really careful with comparing capacity factors. If you're comparing between different wind farms, my advice is between different power production devices, just compare costs. Just compare levelized costs of electricity. Don't compare capacity factors. But it's okay to compare between wind projects if you want to know which wind project is better than another one. So yeah, just to summarize some important numbers, if you just want to use these slides as a reminder, we have the equation for the power in the wind, and for the tip speed ratio, and for the power coefficient, which we talked about. There's two things on here which we haven't talked about yet, which is also quite interesting. There's a thing called technical availability, which is the percentage of operating time. And it's usually like 97% in wind energy. But there's a separate thing called energetic availability, which is actual energy yield divided by the energy yield if you had 100% technical availability. The best way to explain this is, imagine you have 3% downtime, so 3% of the time it's not operating. Imagine in these 3% of the time there's no wind. How much energy you would be losing? You'd be losing no energy because there's no wind. And then the energetic availability would be 100%. But it's actually possible to plan this 3% of the time when there's no wind, and then you actually get 100% energetic availability and not 97%. And then this is just showing a summary of the annual energy production, the full load hours, and the capacity factor. And then we've finished. So I would go on to the exercise unless somebody wants to ask something. First thing I'm going to do while I'm just waiting for you to think if you want to ask some questions, I'm just going to copy the lecture into the folder so you can use it when you're doing the exercise. Day 1, session 2. So I'm just going to put it in there under lecture notes. So it should be uploaded in a second. Let me just, yeah. So is it okay if I explain the exercise and then leave you to, well, you can take a break or you can start doing the exercise, and I'm not going to go into groups because it's not really group work, it's kind of individual work. So you have to open an Excel sheet and you have to do some stuff. But I think we just sit here together and you try to do it. And if you have some questions, just ask me and we can talk about it in a big group as we go along. So the exercise is so it's based on an Enercon 141 wind turbine, which has these different characteristics. So rotor radius, power coefficient, drivetrain efficiency, rated wind speed, density. And it's installed at this location here off the Brazilian coast. Doesn't actually matter what the location is. And so the first part of the exercise is to calculate the power coefficient. No, sorry, that's it. So you just use the equation for power coefficient. It's just the power divided by half rho v cubed a. So you've actually got all the information. Just one tip, the drivetrain efficiency I forgot to mention. Usually the CP, the overall CP is just the drivetrain efficiency multiplied by the rotor CP. So you need to include the 95%. You need to multiply the CP with 95% as well. I can actually put that into the PowerPoint when I've stopped talking. So that's the first task, and then the second task, I would advise you to start doing it in Excel from the beginning, because the second task is to do the same, but for all these different wind speeds. Actually, no, sorry, it's not. Part B is to calculate the power based on the CP at these different wind speeds. So you copy the equation for power, and you just do it for all these different columns up to 14 meters a second. And part C is that above rated wind speed, the power is the same. So this is actually giving you the answer to the first part of the question, by the way, if anyone wants some help. You have to calculate the CP then backwards using those powers, because the power stays constant and the CP then reduces. Then the fourth part is to then, I've given you a wind speed distribution. I've given you a table. You can copy it into Excel. And I say what percentage of the time do you have which wind speed. And then you can, for each of these bins, you can then calculate using the power curve and the frequency distribution, you can calculate the energy. And then you can add it up, and then you should get one value. And then you calculate the capacity factor and the full load hours. That's it. I do actually have the solutions in the presentation as well, so you can cheat if you want, but try to do it yourself and let me know if you need something. Is everyone okay with just doing that now and asking questions if something comes up? Has anyone got any questions before you get started?
Hi, about the maintenance work. How far into the future do you need to forecast the speed to do to conduct the maintenance? Because you mentioned adaptive.
Yeah, it's a good question, and it's a very difficult to answer. So it depends on the company. So some companies, if they have lots and lots of wind farms, they have teams stationed in different locations, and then they can react quite quickly. But if you're offshore, for example, you have to take into account the weather, so you can book the boat to go out, and then the weather could change any minute, and so you need like a few days advance, but you know, like wind speed predictions are really bad more than a couple of days in advance. So it's very difficult to get that right. I think lots of companies use experience and trial and error systems for doing that, but it's definitely an area which can be improved and is being improved.
Okay, thanks.
So did you all get the presentation inside the folder? Has it been
It's here.
uploaded already? Yeah?
Got it.
Okay, it's just that it's easier to copy. Well, you need it really, because then you can copy out the text in these tables into an Excel sheet. Yeah, I'm just gonna be here. Let me know if you want anything, and we'll do, yeah, like in 10 minutes before 5 or 4:45, we'll do a roundup. Yeah, but feel free to tell me if you want to know if the answer's right, or if you want to ask somebody something. Yep. Okay, so I'm going to assume everyone's fine until I hear anything.